8086. Introduction to 8086. Important features of 8086. 8086 is a 16-bit processor having 20 address lines. A maximum of 2 power 20 equal to 1 megabyte can be connected. All registers are 16-bit in length. There are 8 8-bit general data registers: AX, AHAL, BX, BHBL, CX, CHCL, DX, DHDL. It can be operated in two modes with the help of control signal. MN bar MX bar equal to 0 means maximum or multiprocessor mode, equal to 1 means minimum or single processor mode. When processor is reset, control of the program is transferred to FFFF4F0H. It contains 6 bytes of pre-decoding instruction byte queue, by which 6 bytes of instruction can also be prefetched into the processor. At the same time, interval more than one instruction can be at different stages of execution, that is parallel execution of instruction. This process is known as pipelining. Technique involved in 6 bytes of queue is first in first out. There are 9 flags in 8086: D15 no flag, D11 overflow O flag, D10 direction flag, D9 I interrupt flag, D8 T trap flag, D7 similar to 8085, D6 Z, D7 sign, D6 Z, D4 auxiliary carry, D2 parity, D0 carry. Status flags: S Z A C P C Y 0 O, S Z A C P C Y O. Control flags: D I T. D means direction, I means interrupt, T means trapped. It follows one Neumann architecture for memory, but it's segmented memory. But it is segmented memory. 1 MB is segmented into 16 logical segments. 1 MB means 2 power 4 into 2 square 16, that equal 2 power 20. 16 in brackets of 64 KB. Interrupts: hardware NMI, software INTM. Hardware interrupts లో NMI INTR, software లో INTN, N equal 0 to 255, type 0 to type 255. Architecture of 8086: general purpose registers AHL, BHBL, CHCL, DHDL, whereas pointers: stack pointer BP, index registers SI, DI, segment registers ES, CS, SS, DS, instruction pointer IP. So that is mapped to 16-bit ALU flags. Bus interface units has address lines, data lines, BHC bar S7, RD bar, WR bar, INTA bar, comma, ALE, comma, DT bar, R bar, DEN bar. 6-byte instruction queue. Whereas clock, VCC, GND, MN bar, MX bar, decoding circuitry, timing and control unit, control lines. Functional units: bus interface unit, BIU. It contains address conversion mechanism in which two 16-bit registers are used to find out or calculate 20-bit effective of or physical address. It contains 6 bytes of instruction byte queue used for prefetching the instructions or parallel execution, known as pipelining technique. It has different segment registers to hold base address of code, data stack, and extra segments. It makes the processor to communicate with external devices, including memory. That is about bus interface unit. Now, execution unit. It is responsible for decoding the prefetched instruction in BIU. It generates various control signals for BIU and also for operations of processor. It contains different registers like general data registers, pointer and index registers, flag registers. What are general data registers, pointer index registers, flag registers? Memory segmentation. 1 MB of memory is divided into 16 logical segments, each of 64 KB. Okay, now H2 0000H, that is called 64 KB. Whereas base address, indicating starting location of a particular segment which may be present in segment register. Offset address, the distance of actual memory location from base address in a particular segment. It is present in pointer or index registers or BX registers. Physical address, it is position of actual memory location from the beginning of memory. Segments, there are 4 types of segments: Code segments contains code or program. Code segment register CS base address IP offset address. Instruction pointer is similar to program counter which contains offset address of next instruction to be executed. Data segment contains data DS base set address BP SA DA BX offset address. Stack segment contains temporary data SS base address SP offset address. Extra segment contains data ES base address DI offset address. Range of segment address can be from 000H to F4000H. Range of segment address can be from 000H to F00H. Range of offset address can be from 40H to 4FH. F. Register organization General Data Register AX, AHAL, BX, BHBL, CX, CHCL, DX, DHDL. Special purpose registers IP, SP, BP, SA, DA. These are all pointer and index registers. If we come to segment registers CS, SS, DS, ES. If we come to flag register 16-bit. General data registers AX is also called as accumulator. One of the operands in multiplication and division operation must be present in accumulator. BX it is used to hold offset address in data segment. CX used as default counter in instructions like loop, loop Z, loop NZ. DX using multiplication and division operations and also has implicit registers. Flag registers trap TF equal to 1 processor enters into single step execution mode in use execution steps after every instruction such that contents of registers can be verified. Interrupt flag IF equal to 1 maskable interrupts are recognizable by processor direction flag. It is used in string manipulations instructions D equal to 0 auto increment mode D equal to 1 auto decrement mode. War flag overflow flag it is set 1 if result of a signed operation 8-bit on 816-bit is not possible to be accommodated in designation register it is 0 otherwise. Addressing modes sequential flow instructions there are 8 addressing modes immediate addressing mode direct addressing mode register addressing mode register indirect addressing mode register relative addressing mode index relative addressing mode based index addressing mode relative based addressing mode. Control transfer instructions inter segment direct దాంట్లో indirect inter segment direct indirect intra segment if control of the program is transferred within the same segment it is known as intra segment which can be direct or indirect addressing modes. If an 8-bit signed displacement is used there can be plus 127 to minus 128 location possible known as short jump. If a 16-bit signed displacement is used, there can be plus 32,767 to minus 32,768 locations possible known as long jump. Intersegment. If control of the program is transferred from one segment to another, it is known as intersegment, which can be direct or indirect addressing modes. Unconditional jump instructions are used in this type. Microprocessor. It includes ALU, registers, arrays, and control circuits in a single chip. Addition of external ROM, RAM, and input devices makes the microprocessor-based circuit bulky and costly. As microprocessor supports large amount of external memory, they are designed with large number of instructions. Microprocessors are used for designing general-purpose digital computing systems like personal computers. Microprocessor-based systems consumes more power. Microcontroller. It includes a microprocessor, RAM, ROM, and input-output signal lines and a single chip. As there is no need of such external devices, the microcontroller-based circuitry becomes simple and cheap. As microcontrollers operate with small amount of fixed internal memory, these are designed with small number of instructions. Microcontrollers are used for designing dedicated or single-purpose digital computing systems like automatic traffic light control systems. Microcontroller-based systems consumes less power. Brief history of the 8051. External interrupts control on-chip ROM for program code, on-chip RAM, etc, timer 0, timer 1, CPU, OSC, bus control, 4 input-output ports, serial ports. ROM on-chip program space bytes 8051 has 4K, 8052 has 8K, 8031 has 0K. RAM bytes 8051 has 128, 8052 has 256, 8031 has 128. Timers 8051 has 2, 8052 has 3, 8031 has 2. Input output pins 8051 has 32, 8052 has 32, 8031 has 32. Serial port 8051 has 1, 8052 has 1, 8031 has 1. Interrupt sources. 8051 has 6, 8052 has 8, 8031 has 6. 8051 registers. In the CPU, registers are used to store information temporarily. That information could be a byte of data to be processed or an address pointing out to the data to be fetched. The vast majority of 8051 registers are 8-bit registers. In 8051, there is only one data type, 8 bits. The most widely used registers of the 8051 are A accumulator, B R0, R1, R2, R3, R4, R5, R6, R7, DPTR data pointer, and PC program counter. All of the above registers are 8 bits except DPTR and the program counter. In 8051, register A must be involved in the destination for all arithmetic operations. There are 16-bit registers in the 8051 PC program counter and DPT data pointer. PSW program status word register. The program status word PSW register is an 8-bit register. Four of the flags are called conditional flags, mean that they indicate some conditions that the result after the instruction is executed. Those four are CY, AC, P, was CY, AC, F0, RS1, RS0, OV, and so on. P, CY, PSW7, carry flag, AC, PSW6, auxiliary carry flag, F0, PSW5, available to the users for general purpose, RS1, PSW4, register bank selector bit 1, RS0, PSW3, register bank selector bit 2, 0, OV, PSW, overflag, PSW1, user defined bit P, PSW0 not. P ఒకటే PSW not ఒకటే parity flag set are cleared by hardware each instruction cycle to indicate an odd or even number of 1 bits in accumulator. RS1 0, RS0 0, register bank 0, then address equal to 00H to 07H. RS1 0, RS0 1, register bank 1, then address 08H to 0FH. RS1 0, RS0, register bank 2, then address equal to 10H to 17H. RS11, RS01, then register bank 3, address equal to 8H to 1FH. CY, the carry flag. This flag is set whenever there is a carry out from the D7 bit. This flag bit is effected after an 8-bit addition or subtraction. It can also be set to 1 or 0 directly by instructions such as set BC, set BC, and CLRC, where set BC stands for set bit carry and CLRC for clear carry. AC, the auxiliary carry flag. If there is a carry flag from if there is a carry from D3 to D4 during an add or subtract operation, this bit is set, otherwise it is cleared. This flag is used by the instructions that perform BCD, binary coded decimal arithmetic. P, the parity flag. The parity flag reflects the number of ones in the A accumulator register only. If the A register contains an odd number of ones, then P equal to 1. Therefore, P equal to 0 if A has an even number of ones. OV, the overflow flag. This flag is set whenever the result of a signed number of operations too large, causing the higher order bit to overflow into the same bit. In general, the carry flow is used to detect errors in unsigned arithmetic operations. The overflow flag is only used to detect errors in signed arithmetic operations. 8051 register banks and stack. The 8051 microcontroller has a total of 128 bytes of RAM. In this section, we discuss the allocation of these 128 bytes of RAM and examine their uses as registers and stack. RAM memory space allocation is in the 8051. There are 128 bytes of RAM in the 8051. Some members, notably the 8052, have 256 bytes of RAM. The 128 bytes of RAM inside the 8051 are assigned addresses 00 to 07FH. 00 to 07FH. They can be accessed directly as memory locations. These 128 bytes are divided into three different groups as follows. As total of 32 bytes from locations 00 to 1F hexa are set aside for registers in the stack. A total of 16 bytes from locations 20H to 2FH are set aside for bit addressable read or write memory. A total of 80 bytes from locations 30H to 7FH are used for read and write storage, or what is normally called as scratch pad. These 80 locations of RAM are only used for the purpose of storing data and parameters by 8051 programmers. We will use them in future chapters to store data brought into the CPU via input-output ports. Register banks in the 8051. A total of 32 bytes of RAM are set aside for register banks and stack. These 32 bytes are divided into 4 banks of registers, in which each bank has 8 registers. R0 to R7 RAM locations from 0 to 7 are set aside for bank 0 of R0 to R7, where R0 is RAM allocation 0, R1 is RAM allocation 1, R2 is location 2, and so on. Bank 1 uses the same RAM space as the stack. There is a major problem in programming the 8051. We must either not use register bank 1 or allocate another range of RAM for the stack. RAM allocation is 8051 0 to 0 register bank 0, 08 to 0F, register bank 1, 10 to 17, register bank 2, 8 into 1F, register bank 3, 20 to 2F, bit addressable RAM, 30 to 7F, scratch band RAM. How to switch register banks? We can switch to other banks by use of the PSW program status port register. Bits different D3 of the PSW are used to select the set register bank as shown in the table. How the stack are accessed in the 8051? The register used to access the stack is called the stack pointer register. The stack pointer in the 8051 is the only 8 bits byte, which means that it can take values of 00 to WFH. When the 8051 is powered up, the SP registers contains values of 07. Pushing onto the stack. Stack pointer points to the last used location of the stack. As we push data onto the stack pointer SP is incremented by 1. This is different from many microprocessors, notably AX86 processors, in which the SP is decremented when data is pushed onto the stack. Upper limit of the stack. If in a given program we need more than general principle application programs 08 to 1FH is equal to 24 bytes of stack, we can change the SP to point to RAM locations 30 to 7FH. This is done with the instruction MOV SP hash XX. Moreover, 8051 input output programming, the 8051 there are a total of 4 ports for input output process. Examining figure 4.1, note that of the 40 pins, a total 32 pins are set aside for the 4 ports P0, P1, P2, P3, where each port takes 8 pins. The rest of the pins are designated at VCC, GND, XTAL, XTAL2, RST, EA bar, ALE bar are program, and PSEN bar. Input output port pins and their functions. The 4 ports of P0, P1, P2, P3 each use 8 pins, making them the 8-bit ports. All the ports upon reset are configured as inputs, ready to be used as input ports. When the first 0 is written to port, it becomes an output. To reconfigure it as an input, a 1 must be sent to the port. To use any of these ports as an input port, it must be programmed. Port 0. Port 0 occupies a total of 8 pins. Pin 32 39, it can be used for input or output. To use the pins of port 0 as both input and output ports, each pin must be connected externally to a 10k ohm pull-up resistor. This is due to the fact that P0 is an open drain, unlike P1, P2, P3. Port 1 occupies a total of 8 pins, P1 through 8. It can be used as input or output. In contrast to port 0, this port does not need any pull-up resistor since it already has pulling up resistors internally. Port 2 occupies a total of 8 pins, pin 21 through 28. It can be used as input or output. Just like P1, port 2 does not need any pull-up resistors since it already has pull-up resistors internally. Dual role of port 2 in many systems based on the 8051 PT used as simple input output. However, in 8031 based systems, port 2 must be used along with port P0 to provide the 16-bit address for external memory. Port 3 occupies a total of 8 pins, pins 10 through 17. It can be used as input or output. P3 does not need any pull-up resistors, just as P1 and P2 did not. The 8051 provides a total of 5 distinct addressing modes. A CPU can access data in various ways. The data could be in a register or in memory or to be provided as an immediate value. These various ways of accessing data are called addressing modes. 8041 provides a total of 5 distinct addressing modes: immediate addressing mode, registered addressing mode, direct addressing mode, registered and direct addressing mode. In this addressing mode, the source operand is a constant. In immediate addressing mode, as the name implies, where the instruction is assembled, the operation comes immediately after the opcode. Move A, hash 79H, load 79H into A. Move R4, hash 56, load the decimal value 56 into R4. Move B, hash 84H, load 84H into B. Move DPTR, hash, 5678H, DPTR equal to 5678H. Registers addressing mode. Register addressing mode. Register addressing mode involves the use of registers to hold the data to be manipulated. Examples of register addressing modes follow: move A, R naught, copy the content of R naught into A, move R2 from A, copy the contents of A into R2, add A, R5, add the contents of R5 to contents of A, add A, R7, add the contents of R7 contents of A. Direct addressing mode. The RAM has been assigned addresses 00 to 7FH. RAM locations 00 to 1FH are assigned to the register banks and stack. RAM locations 20 to 2FH are set as bit addresses will space to saving single bit data. RAM locations 30 to 7FH are available as a place to save byte size data. Although the entire 128 bytes of RAM can be accessed using direct addressing mode, it is most often used to RAM access RAM locations 30 to 7 of H or not, 40H. Save content of RAM location 40H in R not 56H on A. Save content of A in RAM location 56H. R4, 7 of H. Contents of RAM location 7 of H to R4. Register indirect addressing mode. In the register indirect addressing mode, a register is used as a pointer to the data. If the data is inside the CPU, one registers R0 and R1 are used for this purpose. R2, R7 cannot be used to hold the address of an operand located in RAM. When using the register addressing mode, the result of sign as shown below. Okay, the register indirect addressing mode. The rate of R0, contents of RAM locations whose address is held by R0 into A. At the rate of R1, B, contents of B into RAM locations whose address is held by R1. Indirect indexed address mode and on-chip ROM access. Indexed addressing mode is usually widely used in accessing data elements of lookup tables and is located in the ROM space of the 8051. The instructions used for this purpose is move C, A at the rate of A plus DPTR. The 16-bit registers DPTR and register A are used to form the address of the data element stored in the on-chip ROM. 8051 special function registers SF for address. ACC star accumulator OE0H B register OF0H PSW program status word 0D0H SP stack pointer 81H DPTR data pointer 2 bytes DPL low byte 82H DPL high byte 83H P1 port 1 port 0 80H port 1 90H port 2 80H port 3 0B0H IP interrupt priority control 0B8H IE interrupt enable control 0A8H TMOD timer or counter mode control 89H TSCON timer or counter control 88H T2CON timer or counter to control 0C8H T2 mode timer or counter code mode control 0C9H TH not timer or counter 0 high byte 8CH TL not TTHL. Okay, RCAP T bar C to capture register higher byte, SCON serial control, SBUF serial data buffer, PCON power control. For this reason, the 8051 has another 64 bytes of memory space set exclusively for data storage. This data memory space is referred to as external memory and is accessed only by the MOVX instruction. In other words, 8051 has a total of 128 bytes of memory space, since 64K bytes of code added to 64K bytes of data space gives us 122K bytes. Programming 8051 timers. 8051 has two timers, timer 0, timer 1. These can be used either as timers or as event counters. In this section, we first discuss the timers, registers, and then slow how to program the counters to generate the delays. Basic registers of the timer. Both timer 0 and timer 1 are 16-bit wide. Since the 8051 has an 8-bit architecture, each 16-bit timer is accessed as two separate registers of low byte and high byte time 0 registers. The 16-bit registers of time 0 is accessed as low bytes and high bytes. The low byte register is called as TL0, timer 0 low byte, and the high byte register is referred to as the TH not timer 0 H byte. These registers can be accessed like any other register such as A, B, R0, R1, R2, etc. Timer 1 registers, timer 1 also 16 bits, and 16-bit register is split into 2 bytes referred as TL1 timer 1 low byte and TH1 timer 1 high byte. The registers are accessible in the same way and the registers of timer 0. T mode, timer mode registers. Both timers 0 and 1 use the same register called T mode to set the various time operations mode. T mode is an 8-bit register in which its lower 4 bits are set assigned for timer 0 and the upper 4 bits for timer 1. In each case, the lower 2 bytes are used to set the timer mode and the upper 2 bits to specify the location. D8 to D15, TH0, D0 to D7, TL0 for time 0 registers, time 1 registers, D0 to D7, T1, D8 to D15, TH1. Okay. MSP get C bar T M1 M0 that is the comes in timer 1 run. LSP get C by T M1 M0 that comes in timer 0. Gating control when set. The timer count is enabled only while the INTX pin is high and the TRX count set is pin is set. When clear, the timer is enabled whenever the TRX control bit is set. C bar T timer counter set cleared for timer positions. Input from internal system clock set for counter operation. Input from TX input pin. M1 mode between M0 mode bit 0. M1 M0 mode 0 0 0. 13 bit timer mode 0 1 1. M1 M0 mode 0 1 1. 16-bit timer mode. 16-bit timer account THX and TLX are cascaded. There is no prescaler. 102 8-bit auto reload. 8-bit auto reload timers are counted as THLX. THX holds a value that is to be reloaded in a TLX each time it offers 113 split time mode. Split timer mode. C bar T clocker time. This bit in the T mode register used as the decide whether the timer is used as a delay generator or event counter. It's C by T equals 0. It is used as a time for a time delay generation. The clock source for the time delay is the crystal frequency of 8051 gate. The other bit of the T-mode register is the gate bit. Notice in the T-mode register of figure 9.3 that both timers 0 and 1 have the gate bit. What is the purpose? Every timer has a means of starting and stopping. Some timers do this by software, some by hardware. Some have both software and hardware controls. The timer in the 8051 have both. That start and stop of the digital timers are controlled by the way of software by the timer bits TR0 and TR1. This is achieved by the instructions set TR1 and CL TR1 for timer 1 and set B TR0 and CL for timer 0. The set instruction starts it and it is stopped by the CLR instructions. The instructions start and stop the times as long as gate equals 0 in the T mode register. The 8051 has serial communication capability built into it, thereby making possible fast data transfer using a few wires. Thank you.